Welcome to Module 7, where we bring your Python skills together with the world of databases. Over the next 12 lessons and a final project, you'll learn how real applications store, organize, and protect their data. By the end, you'll be building data-driven programs with confidence. Let's get started. Data is only useful if you can find what you need. Let's master filtering, searching, and sorting. This lesson is about asking precise questions. You'll filter rows with where, combine conditions with and or, search text with like, match ranges and lists with between and in, sort with order by, and cap results with limit. Here's your toolkit of operators. Equals and not equals for exact matches. The comparison operators for numbers. And or to combine conditions, like for text patterns. In to match a list of values, and between for ranges. Mix and match to pinpoint any rows. Putting it into Python, we pass the search term as a parameter, and let SQL do the work. This function filters staff by department, sorts them by salary from highest to lowest, and limits the results to the top 5. Clean, safe, and powerful. Recap. Where filters rows, and or combine conditions, and like searches text with percent and underscore wildcards. In and between match lists and ranges. Order by sorts your results, and limit controls how many come back. Real data lives in many connected tables. Let's learn to bring it back together with joins. In this lesson, you'll combine data from related tables using joins. We'll see why data is split up, how foreign keys connect it, the difference between inner and left joins, and how to read joined results in Python. There are 2 joins you'll use most. An inner join returns only rows that match in both tables, the overlap. A left join keeps every row from the left tables, filling in nulls where there's no match. The ON clause tells SQL which columns connect, and aliases keep it readable. Here's the difference in action. The inner join lists only customers who have orders, pairing each name with its order total. The left join keeps every customer, even those with no orders. They simply show null. The ON clause matches each order to its customer. A joined query returns columns from several tables in one combined row. In Python, you run the join and then unpack each row straight into named variables. Here, name and total. One query. Neatly formatted output. Recap. Related data lives in separate tables connected by foreign keys. Inner join returns only matching rows, while left join keeps all rows from the left. The ON clause defines the connection, and aliases keep your queries clean. What happens when something fails halfway through? Let's make our data bulletproof with transactions and error handling. This lesson keeps your data correct under pressure. You'll learn what a transaction is, how commit and rollback work, why some operations must be all or nothing, and how to catch database errors gracefully with try, except, and finally. A transaction has a clear life cycle. You begin, execute your operations, and check for success. If everything worked, you commit, and all changes are saved together. If anything failed, you roll back, and it's as if nothing happened. All or nothing. This is the classic example. Moving money means subtracting from one account and adding to another. If the second step fails after the first succeeds, money would vanish. So we wrap both in a try block, commit only if both succeed, roll back on any error, and always close the connection. Some errors you'll want to catch by name. An integrity error means a duplicate key or broken constraint. An operational error might mean a locked database or a missing table. Whatever the cause, roll back partial changes and always close your connection in a finally block. Recap. A transaction groups related operations. Commit saves them all at once. Rollback undoes them on failure. Transactions are all or nothing. Try and except catch database errors. And finally, always closes the connection. Let's step up to a professional, production-grade database, PostgreSQL, and connect it to Python. In this lesson, you'll connect Python to PostgreSQL using the psycopg2 library. We'll see what a production database offers, how to connect with credentials, the placeholder style it uses, and when Postgres is the right choice over SQLite. In code, the differences are small but important. SQLite uses the built-in SQLite 3 module and a local file. Postgres uses psycopg2 and connects to a server with credentials. SQLite's placeholder is a question mark. Postgres uses %-s. Otherwise, the SQL is nearly identical. Here's a real connection. We pass the host, database name, user, and password to psycopg2. Then we run an insert using %'s placeholders, commit, and close. If you know SQLite, you already know 90% of this. Recap. PostgreSQL is a production database server, and psycopg2 connects Python to it. Connections need host, user, password, and database. Placeholders use % and serial auto-generates keys, but the core SQL stays the same. What if you could work with your database using plain Python objects instead of SQL strings? That's the power of an ORM. This lesson introduces object relational mapping with SQL Alchemy. you'll learn how classes map to tables, how to define columns as attributes, how to create your schema, and how to add and query data using sessions, all in Python. Here's the shift. With raw SQL, you write query strings by hand, powerful but verbose and error-prone. With an ORM like SQL Alchemy, a table becomes a Python class and a row becomes an object. You add a student object. SQL Alchemy writes the SQL for you. On the left, we define a student model, a class where each column is an attribute. On the right, we create the engine, build the schema, and open a session. Adding a student is just adding an object, and querying uses familiar Python syntax with filter. Recap: an ORM maps classes to tables and objects to rows. Columns become class attributes. Create_all builds the schema, and a session adds, queries, and commits your data. Best of all, you filter using Python instead of writing SQL strings. Databases change over time. Our final tool, Alembic, lets you evolve your schema safely, like version control for your tables. In this lesson, you'll learn about migrations, tracked, reversible changes to your database structure. We'll see why schemas change, how Alembic works with SQL Alchemy, and how to auto-generate, apply, and roll back a migration. Why bother with migrations? Because schemas evolve as features grow, and you need to change structure without losing data. Migrations give you a versioned history that's reversible and team-friendly. Everyone applies the same changes, and you can upgrade forward or downgrade back. The workflow is 4 commands. Initialize Alembic once. Auto-generate a migration, and it detects what changed in your models. Apply it with upgrade, and if something breaks, downgrade to undo it. Each migration file has an upgrade and a downgrade function. Recap: a migration is a tracked schema change, essential as your app grows. Alembic manages migrations for SQL Alchemy. Auto-generate detects model changes, upgrade applies them forward, and downgrade rolls them back safely. Now let's bring everything together. Your final project is a complete student management system, a real application built from every skill in this module. Your mission is to build a command-line student management system. It will design a student schema, offer full CRUD through a menu, support search and sorting, use safe parameterized queries, stay organized in reusable functions, and handle errors gracefully. Keep the project clean with 3 files. Database.py holds the connection and all your data functions. App.py runs the menu and talks to the user. And students. DB is the database file itself, created automatically. Separating data from interface makes the project easy to grow. Inside database.py, each operation is a small, focused function. Add _student and list _students handle creating and reading. Update _grade and delete _student handle the rest. Everyone uses a with block and parameters. The safe patterns you've practiced all module. App.py drives the experience. It creates the table, then loops, showing a menu and reading the user's choice. Each choice calls the matching database function. This clean separation, interface here, data logic there, is exactly how professional apps are structured. Once it works, make it yours. Add a courses table linked by a foreign key, track grades over time, add richer search, move to PostgreSQL, refactor with SQL Alchemy, or wrap it in a web interface. Every idea here uses a skill from this module. Congratulations! You've come a long way. You can now design schemas, run safe CRUD, join and relate data, protect it with transactions, and use professional tools like PostgreSQL, SQL Alchemy, and Alembic. You're ready to build real, data-driven Python applications. Well done! Here's the road ahead. We start with the fundamentals, what databases are, and how they're structured. Then we connect Python, run real operations, and learn to search and join data. Finally, we move into professional territory. Transactions, Postgres, ORMs, and migrations. Each lesson builds on the last. Think of the module in 4 stages. First, foundations, the concepts and SQL basics. Next, Python with SQLite, where you'll do most of your hands-on practice. Then reliability, with transactions and PostgreSQL. And finally, the professional tools that teams use every day. Follow this path and everything connects. Let's begin at the very beginning. What a database actually is, and why nearly every application you use relies on one. In this first lesson, our goal is simple. Understand what a database is and why it matters. We'll see how databases compare to plain files, what kinds of data they store, and where they show up in the real world. No code yet, just the big picture. A database is simply a structured place to store and manage data. Think of it as a smart, organized storage system. Instead of scattering information across random text files, everything lives in tidy tables you can search, update, and protect. This table of customers is a perfect example. So why not just use files? For a handful of records, files are fine. But as data grows, files become slow and messy. Databases shine when you need to search quickly, handle relationships, support many users, and keep data secure. This is why real applications almost always reach for a database. Databases are everywhere. Your bank uses one for accounts and transactions. Schools track students and grades. Online stores manage products and orders. Hospitals, social media, inventory systems, all powered by databases working quietly behind the scenes. Throughout this module, we'll work with 3 tools. SQLite is lightweight and built right into Python, perfect for learning. PostgreSQL is a professional server used in production. And SQL Alchemy lets us work with databases using Python objects. We'll meet each one in turn. Let's recap. A database stores and organizes application data, and it beats files once data grows. Relational databases use tables made of rows and columns, and SQL is the language we use to talk to them. SQLite is our beginner tool. PostgreSQL is the professional one. Now that we know what a database is, let's look inside one, at tables, keys, and the relationships that tie everything together. In this lesson, we'll unpack how relational databases organize information. You'll learn about tables, rows, and columns, and 2 very important ideas: primary keys and foreign keys. These are what let separate tables connect to one another. A table looks a lot like a spreadsheet. Each table stores one kind of thing. Here, students, every row is a single record, every column is a field like first name or grade, and each cell holds one value. Get comfortable with this structure. Everything builds on it. 2 keys do the heavy lifting. A primary key uniquely identifies each row. It answers, "Who am I?" A foreign key points to another table's primary key. It answers, "Who do I belong to?" Together, they let tables reference each other reliably. The most common relationship is one-to-many. One customer can have many orders. One teacher, many courses. One author, many books. Notice how each order carries the customer's ID. That's the foreign key, linking it back to exactly one customer. Now that we understand relationships, let's write the code to create them. We use SQL commands like create table. Note how the orders table uses a foreign key to reference the customer's ID in the customers table. NotNUL ensures that an order must be associated with a valid customer. A few rules keep your database clean. Each table should describe one kind of thing, each row, one record, and each column one value. Use keys to connect tables, avoid repeating data, and give everything clear names. Good design now saves you real pain later. To recap our look at relational tables, we store data in rows and columns. We use primary keys to identify records, and foreign keys to create relationships between tables. Following design rules ensures your data stays organized and reliable. Now it's time to speak the language of databases. Let's learn SQL. The fundamental commands you'll use to create, read, update, and delete data, often referred to as CRUD operations. This lesson covers the core SQL commands. You'll learn to create tables and insert records, read that data back, filter it, sort your results, and perform updates and deletions safely. These commands are the building blocks of every data-driven application. SQL revolves around the CRUD acronym: create, read, update, and delete. Each corresponds to a specific command: insert, select, update, and delete. Master these 4 basic operations, and you'll be able to build most common features in your applications. First, define your table structure with create table, specifying column names and types. Then, populate it with insert into. Note that the order of the columns and the order of the provided values must match exactly for the insertion to succeed. The select command is how you retrieve data. You can filter results with where, search for text patterns with like, change the order with order by, and limit the number of returned rows with limit. Combining these gives you powerful tools for querying your data. Here is a critical safety tip. Always include a where clause when performing an update or a delete operation. Without it, you will unintentionally modify or erase every single record in your table. Targeted commands prevent accidents. Let's summarize our SQL basics. Create table sets up your schema, insert adds records, and select reads them. Use where, like, order by, and limit to refine your queries, and always protect your table data by pairing update and delete with a specific where condition. Now that you know SQL, let's learn how to run those commands directly from Python. We'll explore how to establish a connection, use a cursor, and execute queries effectively. In this lesson, we will cover the essentials: understanding the database connection and cursor, how to execute SQL within your Python code, how to retrieve results, and why using commit is essential for saving your work. We'll also cover writing safe, parameterized queries. Think of it this way: your Python application needs to open a door to the database. The connection acts as that door, while the cursor is the messenger that carries your SQL commands to the database and brings back the results. To work with a database in Python, you'll import SQLite 3, create a connection, and retrieve a cursor. Once you execute your SQL command, remember to call connection.commit to save your changes, and connection.close to free up system resources. It's a standard and safe workflow. Security is paramount. Never build SQL queries by combining strings with user input. This creates a vulnerability called SQL injection. Instead, use question mark placeholders in your queries and pass the inputs as a separate tuple. This ensures the database treats your user input only as data, never as code. Now that we know how to send queries, let's learn how to get our data back. After running a select command, you'll need to fetch the results from your cursor. Use fetchAll to grab every matching row at once, or fetchOwn to retrieve just a single row when you only need one. A great trick is to use a with block. By wrapping your connection in one, Python manages it for you, automatically committing your changes if everything goes right, and closing the connection when you're finished. It makes your code cleaner and significantly reduces the risk of forgetting to save. We've covered the basics. Remember, the SQLite 3 module is built into Python. A connection acts as the bridge to your database, and a cursor is the tool you use to run your commands. Parameterized queries are your best friend for security, and commit ensures your data is actually saved. Let's move to Lesson 5, where we'll start building real, persistent data applications using SQLite. It is the perfect tool for learning in small projects, since it is completely file-based and requires no complex server setup. In this lesson, we will focus on taking your skills to the next level. You will learn to manage databases, work with tables, and handle every step of the CRUD process: create, read, update, and delete. We'll wrap it all together by building a functional employee manager application. It is important to understand how SQLite fits into the broader picture. SQLite is a lightweight, file-based database, which makes it incredibly easy to use locally. PostgreSQL, on the other hand, is a powerful server-based system built for heavy, multi-user environments. Fortunately, the SQL you learn here works for both. For our employee manager, we will create clean, reusable functions to handle our core logic. By separating our adding and searching operations into distinct functions and passing values as parameters, we keep our code readable, maintainable, and most importantly, secure against injection attacks. As you build your applications, follow these best practices. Always parameterize your inputs, commit your changes explicitly, use with blocks for connection management, and always pair updates or deletes with a where clause. Organizing your logic into functions will keep your codebase clean and professional. To recap, SQLite is a local file-based database built right into Python. When you connect, you open that file, and you use a cursor to execute your SQL commands. Always use create table if not exist to stay safe, and remember that organizing your database code into functions is the secret to reusable, clean code. Now that we have covered the basics, let's dive into the core operations that make any database useful. Every data application relies on CRUD: create, read, update, and delete. Let's learn how to implement these consistently. In this lesson, we will build a task management application from the ground up. You will learn what CRUD means, how it maps to real-world features, and how to organize your code into reusable functions that handle every action, from creating tasks to deleting them. Here are the 4 CRUD actions side by side. Use insert to create, select to read, update to modify, and delete to remove. By mastering these 4 commands, you unlock the ability to manage any data within your applications effectively and securely. When performing updates or deletes, you should check cursor.rowCount. This attribute tells you exactly how many rows were modified. If it returns 0, it means nothing happened, which is a great way to detect if a record was missing without crashing your program. Finally, avoid common pitfalls. Always create your tables first. Never forget the where clause on destructive operations, and always validate your user input. With these tips, you'll be writing professional, reliable database code. Let's wrap up this lesson and start building.